Now let's recall the idea of the projection, which I told you some time ago was really, really important. And right here is one of your applications of the idea. Okay, U in this direction, W in this direction. There's an angle, theta here, that's related to the dot product, right? Okay? In other words, the dot product of U and W is the product of the magnitudes of these two vectors times the cosine of this angle. And you've always got to keep that in mind and all of the implications of that thing. Okay, now, the projection of U on W, you just project U perpendicular to W if U happens to be, if theta happens to be greater than 90 degrees, U's going to have a component that goes back this way, so you might have to extend W with a dotted line. But I'm just going to sketch out the situation when theta is positive because we don't want to digress too far. Okay, so here's your projection vector. That projection vector has a magnitude. The magnitude of that projection vector is the length of this side of this triangle. And what's the length of this side of this triangle? Well, it's the length of this side times the cosine of theta. And y'all are very good with triangle trig, so you understand that. And the magnitude of this vector is, of course, the magnitude of U. So the magnitude of the projection, the length of this side is magnitude of U times the cosine of theta. Now, the dot product is magnitude of U times magnitude of W times the cosine of theta. So, okay, now this double arrow here represents the length of this side. It's magnitude of U times cosine theta. It's actually the magnitude of the magnitude of U cosine theta, because cosine theta could be negative, and we just want to look right now at the length of that side. If theta is greater than 90 degrees, it's not difficult to understand what happens, and I leave that to you to sort out. But the magnitude of U cosine theta is what? It's just the magnitude of U dot W over the magnitude of W. Why? I didn't write down the reason. You should be very clear that the U dot W is magnitude of U times magnitude of W times cosine theta. So when you divide by magnitude of W, you're left with magnitude of U cosine theta. Okay? And then that happens to be equal to the magnitude of U dot W if the magnitude of W is 0. Now I'll put the equal sign in red here, so it doesn't look like this is actually always equal to this, and I'll circle it, okay? So under the special condition that the magnitude of W is 1, the projection is just U dot W. Well, we're going to apply that here. A parallel is just the projection of the acceleration vector on the velocity vector. Okay, and we could project it on the velocity vector. We could take this r prime of t or v of t vector. We could project this vector, the a of t, this vector, the a of t vector, onto this vector. If we did, we would take the dot product and then divide by the product of the velocity or r prime vector. Okay. However, we've got the unit tangent vector sitting here where we've already divided by the magnitude of the velocity vector. Okay. And we know now that the unit tangent vector is a unit vector. We wouldn't call it unit tangent vector if it wasn't, and it wouldn't be if we hadn't divided the vector by its magnitude, but we did, so it is. Now, U dot W then is sufficient. Okay, we just take our acceleration vector and dot it with our unit tangent vector, and we get the magnitude of the projection. Okay? Now, there's a little more to it because this dot product might come out negative, but in any case, and you think through that possibility, if I multiply this by the unit tangent vector, then I have a vector that's in the direction of the unit tangent vector, so it's in the direction of the velocity, and its magnitude is equal to the component of the acceleration in that direction. Okay? Now this means, for example, if I'm driving around a curve, my direction of motion is always straight ahead, wherever straight ahead happens to be as I go around that curve. Okay? I have two acceleration components. If my foot is on the gas, if I'm speeding up, then I have an acceleration component in my direction of motion. Okay, that acceleration component doesn't affect any acceleration perpendicular to my direction of motion, but my centripetal acceleration, the acceleration I need to change direction, is perpendicular to my direction of motion. So my acceleration typically has two components. If I'm speeding up or slowing down, I have a non-zero acceleration in the direction of my unit tangent vector, which is straight ahead. And I have a component perpendicular to that that causes me to change direction. Okay? Or you could say it's a result of the centripetal forces, which is what causes me to change direction. If you want to split hairs on it, and that's okay. Okay, well, now let's talk about how you get a vector perpendicular to that component. Let's go over to this picture. Here's U, here's W again. I didn't bother putting theta in. We know how to calculate the projection. Okay, and the projection is what I'll call U parallel. Now U doesn't stand for unit. U is just any vector, W is another vector. I'm going to run out of letters one of these days, okay? Now, the parallel component of U, the component of U that's parallel to W, is this vector. So what's the U perpendicular, the component of U that's perpendicular to this vector? Well, the two components of U have to add up to U. That's what I mean by components. So the component of U in this direction and the component of U in this direction have to add up to U. What's that tell us? Well, it tells us that the parallel component that I'll call U parallel plus the perpendicular component that I'll call U perpendicular, and call it that over here too, has to equal U. Well, we've got a way here where we've actually calculated the parallel component of the acceleration, and we have the acceleration vector. So we know this and we know this for the acceleration. How do we get this, the perpendicular component, which is what we're asked to do here? If this plus this equals this, then this, which is what we want to find, equals this minus this. That works for vectors. You've proved it, or you should have proved it, that vector addition and that vector addition, subtraction, multiplication, etc. behave just like they would if you just had numbers. So that here's your perpendicular component. So that the perpendicular component of the acceleration is just the A, this vector, minus the A perpendicular, this vector. Now this vector has this whole denominator here, and this one doesn't, so you got to do a common denominator, and it does get messy, but it's easy. Doesn't mean it's easy to get it right. It's easy to write it down. It's easy to show what the calculation is. It's a little harder to get the calculation right because there's a lot of algebra involved, but you need to be able, your algebra needs to be up to at least this. Okay? And as I've said, it should also be up to taking the derivative of your unit tangent vector, which is quite messy. You wouldn't want to then try to take the derivative of that, as I've said in class, as opposed as I am to the use of calculators and computer algebra system the first 2 years of an undergraduate engineering type program. That would be an appropriate point at which to go. Not to take the derivative of your unit tangent vector. You should be able to do that. It's a little daunting, but you can do it. But the derivative of that, and it's not, that derivative isn't usually very important anyway, but if you had to take a derivative that complicated, I would think you were justified in going to a computer algebra system, because your chances of getting that derivative right are fairly low until you've had a whole lot of experience and know exactly how you need to keep your bookkeeping, because it's really more a bookkeeping problem than a math problem at that point.